Today, we're going to break down a story many of us think we know, the Challenger disaster. But this isn't just a history lesson. It's a really powerful and, honestly, chilling story about how even the most brilliant systems and the brilliant people inside them can go terribly, terribly wrong. 73 seconds. That's all it took. On the morning of January 28th, 1986, the Space Shuttle Challenger was just gone, torn apart in the sky. Now, the immediate cause, sure, it was a technical problem. But the real story, the reason this still matters so much today, is way more complex. It's a story about culture, about pressure, and about warnings that were heard but not listened to. And that really gets us to the heart of it, doesn't it? This is the central question we're digging into. How could a flaw that was not only known but was actively being argued about the night before launch still lead to a national tragedy on live television? It's like a detective story, and we're going to follow the clues. Okay, so to understand why it all happened, we first have to get crystal clear on what happened. We have to start with the physics, with the hardware itself. It all boils down to a tiny, incredibly important component meeting its absolute worst enemy, the cold.
And that component was the O-ring. Now, don't think of a simple rubber band. These were highly engineered gaskets, and their job was absolutely critical. They sealed the massive joints on the solid rocket boosters to keep the super hot, high-pressure gas from escaping. A simple job, in theory, but one with zero margin for error.
So, what went wrong? It was a domino effect, a terrifyingly fast chain reaction. That morning, it was freezing, way colder than any shuttle had ever launched in before. The cold made the O-rings stiff, almost brittle. So at ignition, they didn't flex and seal the joint like they were supposed to. In milliseconds, hot gas just blew right past them. This created a jet of flame that basically acted like a blowtorch, and it cut right into the giant external fuel tank. And from there, it was. And here you can see the huge gap between the plan on paper and the reality of the launch pad. The design assumed these O-rings would be perfectly elastic, that they'd seal instantly. But the cold, hard reality, which they knew from tests, was that below about 12 degrees Celsius, they got sluggish. They didn't work right. On launch day, the temperature was hovering right around freezing. This wasn't a mystery. It was a known vulnerability. And this, right here, is where the story pivots from a technical failure to a human one. The engineers who actually built these rocket boosters at a company called Morton Thiokol, they saw the freezing temperatures and they knew the danger. The night before the launch, they were on the phone, practically pleading with NASA management to postpone. They didn't just have a hunch, they had data, and they made their recommendation incredibly clear. Do not launch. So the big question is, why didn't that warning work? And to answer that, we have to move away from the hardware and into the culture of the organization. We need to talk about a really powerful and dangerous idea that sociologist Diane Vaughan later identified as the true root cause: the normalization of deviance. Now, normalization of deviance sounds academic, but it's a terrifyingly simple idea. It's not about bad people doing bad things. It's a slow, creeping process. It's what happens when something goes wrong, a technical glitch, an anomaly, but you get away with it. And then maybe it happens again, and you get away with it again. Slowly, over time, the abnormal starts to feel, well, normal. The unacceptable becomes acceptable. And this is exactly what had been happening at NASA. They had seen O-ring damage on previous flights, but because nothing blew up, they didn't see it as a sign of a catastrophic design flaw. Instead, it was just reclassified as an acceptable risk. And this is the craziest part. The whole burden of proof got flipped upside down. Instead of NASA managers having to prove it was safe to fly, the engineers were challenged to prove with 100% certainty that it was unsafe. And of course, you can't prove a negative. So the launch went ahead. This table just lays out the intense pressure cooker they were in. The benefits of launching on time, they were immediate, they were visible, they were guaranteed. You hit your schedule, you make your bosses happy, the program looks good. But the costs of failure, they were abstract. They were in the future. They were just a probability. It might happen. But hey, it hasn't happened yet. This created a huge psychological bias to just push forward and discount those warnings from the engineer. In the aftermath, a presidential commission was set up to figure out what went wrong. And in the middle of all the complex testimony and the finger-pointing, one person cut through all the noise with a demonstration that was just stunningly simple and brilliant. You have to imagine it. The commission was drowning in engineering reports, charts, data, managerial jargon. And the sheer complexity of it all was actually hiding the very simple truth at the heart of the disaster. A piece of rubber got too cold.
And that's when Richard Feynman, the famous Nobel Prize-winning physicist, did his thing. During a televised hearing, he got a small clamp and a piece of the O-ring material, and he just dunked it in a glass of ice water right there at the table. A few moments later, he took it out, released the clamp, and showed everyone how it failed to spring back. It had lost all its resiliency. In one simple, dramatic moment, he showed the entire world the physical cause of the disaster. As he later wrote in his report, "Nature cannot be fooled." So, after all of that, what did we actually learn? Well, the Challenger disaster wasn't just a tragedy. It was a genuine watershed moment that completely forced a rethinking of safety and risk, with lessons that are frankly more relevant today than ever. First, there were concrete physical changes. The rocket boosters were totally redesigned with better joints and heaters. But just as important, the culture started to change. Launch rules were made stricter, new independent safety officers were given real authority to stop a launch, and maybe most importantly, they created channels to protect engineers who had dissenting opinions.
And on a conceptual level, Challenger taught us something incredibly important. Reliability is not the same thing as safety. The shuttle had flown 24 times successfully. It seemed reliable, but it was never truly safe because it had this hidden catastrophic flaw just waiting for the right conditions to show up. It's a huge lesson. Repeated success can actually hide a very deep and very real danger.
And you know, this lesson has echoed way beyond the world of aerospace. The frozen O-ring has become a powerful metaphor in all sorts of high-stakes fields. You see it in medicine, with early warning signs in a patient that get ignored. You see it in finance, with small market oddities that happen right before a major crash. You even see it today in tech, with AI systems being rolled out without anyone really knowing how they'll behave at their limits.
But here is probably the most sobering lesson of all. 17 years later, in 2003, we lost another shuttle, Columbia. And when the investigators looked into it, they found that even though the technical cause was completely different, the root organizational causes, that normalization of deviance, the pressure to stick to the schedule, the silencing of engineering concerns, were shockingly, tragically similar. Fixing the hardware is never enough if the culture doesn't truly change.
And we can never, ever forget the true cost of this failure. It was 7 lives, including Krista McCauley, who was about to be the first teacher in space. The entire shuttle program was grounded for almost 3 years. And the public's trust in NASA, an institution that really represented the best of us, was shattered. When you boil it all down, you get to this one powerful truth. Challenger wasn't a catastrophe that happened because of ignorance. It happened because of the disregard of what was already known. The data was there. The warnings were clear. The physics was undeniable. And that leaves us with a final, really important question to think about. The Challenger disaster proved that the biggest danger we face isn't what we don't know. It's the arrogant confidence that we can somehow negotiate with reality, that we can bend the laws of physics to meet a deadline or a budget. So the question we have to ask ourselves is, where in our world today are we making that same dangerous negotiation?